Hi and welcome to Specialist Maths Unit 1, Topic 1, Video 11, and this video will be about the pigeonhole principle. It's just a small dot point within the syllabus, and the questions that come about from the pigeonhole principle will breach into maybe the complex familiar, but the concept's really important, and it's something that is likely to be assessed in some of your early assessment. So, firstly, the principle, the idea of the pigeonhole principle. If n plus 1 pigeons are placed in n holes, then there's at least one hole with 2 pigeons. That's the concept. So the concept is that if you have spaces to put something and a certain amount of objects to put in them, then we can guess, or we can mathematically work out what the minimum number of things that must be in at least one of the holes. Now, obviously, in this case, if you had 10 pigeons and 9 holes, you may end up with 10 pigeons in one hole. But what we're saying is that 10 pigeons and 9 holes means at least one hole must have 2 pigeons. And this has really important and this has really important ramifications on some of our work to do with probability and combinations and permutations. So I've changed it a little bit in the second pink box there. If n plus 1 objects are placed in n holes, then there is at least one hole with 2 objects. Obviously, the concept is built around the idea of pigeons and pigeonholes, but we're talking about objects here, so it could be anything. So let's have a look at the application. If you have 12 pens, 4 are red, 4 are blue, and 4 are black, how many pens must you choose to guarantee at least 2 pens of the same colour? And how about 3? So in this case, the question doesn't look anything like the pigeonhole principle. I can see that. What we need to determine is what represents the holes and what represents the pigeons. So in this case, the holes are the colours, and the pigeons, or the objects, are the pens. So we're saying, how many pens must we choose to guarantee at least 2 pens of the same colour? Well, our holes are here. There's 1, 2, that's the worst hole ever, 3, and they are red, blue, and black. I can't separate red and blue and black. Red, blue, and black. So if I pick 1 pen, it might be red. And if I pick 2 pens, well, I might have a blue one as well. 3 pens, I might have a black one. In fact, sometimes it's a good idea to think about the minimal application. What's the maximum number of pens that you could pick and still not have 2 pens of the same colour? In this case, if you chose 3 pens, there is a chance you still might not have 2 pens of the same colour. But the 4th pen will guarantee that you've got at least 2 pens of one colour. So the pigeonhole principle here gives us an answer of 4. And equally, if we carry this on, what about at least 3 pens? Well, what if you filled the holes up to 3? That would be 6 pens, which means that the 7th pen must mean that we have at least 3 pens of the same colour somewhere. One of them must be at least. So let's have a look at generalising a bit further. If mn plus 1 objects are placed into n holes, then at least one hole contains n plus 1 objects. Okay, now you can't see me, but I'm rubbing my head because that is really a little bit complex. But let's consider it numerically. Let's say m is equal to, 6, and n is equal to 10. Then we're saying if there are 61 mn plus 1 objects and they're placed into 10 holes, well then at least one hole contains 7 objects. And we can see that that's true. So it's all about this plus 1. If mn objects are placed in n holes, well then every hole could potentially have m objects, which means if you have one more object, then one of the holes must have at least m plus 1 objects. Now they could all go in one hole, but that still matches that criteria. So that's how it works. I really strongly urge you to have a look at this and really think about what's going on. Now here's another mathematical principle, and that is the ceiling of a number. So we'll have a read through this together. If you choose x objects for n holes, then you can calculate the ceiling of that number. So the ceiling is just a rounding technique, essentially. It just means that whatever happens, we round up. So x over n, ceiling notation, is like brackets. It has that top bit, so I'm still on highlighter, top bit, and down. Top bit and down, but has no bottom bit. And it's that top bit that represents the ceiling of that fraction calculation. So if I'm choosing 7 objects for 3 holes, 7 divided by 3, 7 objects in 3 holes means I have 2 in each hole. That's the 2. But I've got a little bit left over, which means that the ceiling is 3. There must be 3 in at least one hole. If I'm choosing 121 objects for 20 holes, 121 divided by 20 is 6.05. The ceiling of the number 6.05 is 7. There must be at least 7 in one hole. So there's the basic principles of the pigeonhole principle taken right to the end. So let's have a look at a couple more examples. Example 2, 25 students in a class achieve A, B, C or D on an exam. Prove that at least 7 scored the same grade. So the first way to approach this is to go back to our traditional understanding and define n, which is the number of holes, as 4. Our n values are here. And then to define x as the number of objects as 25, and then just do our ceiling of x over n is equal to the ceiling number of 25 over 4, which is the ceiling of 6.25, and that of course is 7. So our ceiling is 7. Now another approach here is that we could look at our second pigeonhole principle variant. So I'll just do this in purple, and that is to say, well, our n is equal to 4, and we're trying to get 7 which as our minimum, but we can see here that mn plus 1, it doesn't have to be plus 1 because 25, it could be 26 or 27 and still get a ceiling of 7, is equal to 25, which leads to m equals 6 and m plus 1 equals 7. So going back to our proof earlier, we've got our mn plus 1 objects are placed in n holes, at least one hole contains m plus 1 objects. Well, m plus 1 is 7 objects, so at least one hole contains 7 objects. That's another way around you could do it, although I think you'd probably agree that this is a little bit more crisp and a little bit more easy to work with. Okay, we're going to finally look at example 3, which is not quite as trivial and offers us a complex familiar or even maybe bordering on complex unfamiliar example. If 168 three-digit numbers are selected, prove that it is possible to determine 8 of them which have the same digit sum. So when we talk about digit sum, let's take a 3-digit number. Let's say, so for example, 371. The digit sum is 3 plus 7 plus 1, which in this case is equal to 11. So we want to show that at least 8 of them have the same digit sum. And it could be more, there could be multiple combinations of 8, or in fact, well, maybe not 168, but certainly you could have a larger number than 8 with the same digit sum. So let's consider the digit sums. Now, it's a 3-digit number, and that means that the lowest 3-digit number is 100, and the highest 3-digit number is 999, which means that our digit sums, the possible digit sums are 1, and then 2, 3, 4, so on and so forth, all the way through to 25, 26, 27, which is at 999. Okay, now how do we get a digit sum of 1? The only way of getting a digit sum of 1 is with 100. Even if we change this to 010, that technically is actually a 2-digit number, so it doesn't count. So there's only one way, so I'll make this a table. There's only one way of getting a digit sum of 1. Now the digit sum of 2 could be 200, or it could be 101, or it could be 110. So there's 3 ways of getting a digit sum of 2. And a digit sum of 3 could be 300, could be 201, could be 210, could be 102, could be 120, or it could be 111. So there's 6 ways of getting a digit sum of 3. And it actually works in reverse as well. 999 is the only way of getting a digit sum of 27. There are 3 ways of getting 26 and 6 ways of getting 25. So have a play with that if you want to. But this is really important because that means that those 6 numbers are already out. You cannot get 8 variations of a digit sum of 1 or 2 or 3 or 25 or 26 or 27. Because the problem we have here is that the standard student's probably immediately going to go to 168 over 8 and look at the ceiling. But the problem is 168 over 8 is equal to 21. Sorry, not 168 over 8. My apologies. There's 27 possible digit sums, so 168 over 27, and look at the ceiling of that. And the problem is 168 over 27 is, well, it's equal to 27 times 6 is 162, so it's basically 6 and a bit, 6 point something something, and so the ceiling of that is equal to 7, not 8. That's our problem. But when we do this analysis, we realise that 10 of these numbers we kind of have to take out, and 10 of these possibilities we kind of have to take out, which leaves us with, and this is a worst case scenario, the worst case scenario is that you might be left, you might have all of these used, which means that we've got a total of 20 used, leaving us with 148 numbers. That's the worst case scenario. And because we have 27 numbers available, 27 digit sums, 1 to 27, but we've used up 6 of them, 1, 2, 3, 4, 5, 6, it means that we have 21 digit sums left. So we've got 148 numbers, they're our objects, and 21 is our number of digit sums, so these are our wholes, which means that's n. So now our new calculation will be, what is the ceiling of 148 over 21? And the ceiling of that is 8 and 1 over 21, my apologies, 7 and 1 over 21 ceilinged, and the ceiling of that is 8. So there must be 8 in at least one of them, but we had to do the original and the initial analysis that digit sums 1, 2, 3, 25, 26, 27 really had to be removed from that grouping. So there's our example 3, a complex, familiar, complex, unfamiliar type example, but that's also the concept of pigeonhole principle. All the best.